Here's another example of integration by parts. Let's find the integral of 5x squared minus x in parentheses times e to the x dx. This is another integral that we can tell integration by parts would be useful for because we see that the integrand is a product of two apparently unrelated functions, a polynomial and an exponential function. There isn't a reasonable choice for a substitution here, because these two functions are totally unrelated. So a product of unrelated functions means that integration by parts is a good choice. Remember that our formula is the integral of u dv equals u times v minus the integral of v du. So if we can choose a u and a dv whose product makes up the original integrand, then we'll be able to rewrite this whole expression using the formula and hopefully end up with a new integral that's easier to solve. As usual, for choosing our u, the best thing to do is choose the u first, and whatever's left over will be the dv. For choosing our u, there are two priorities. The first priority is if any of the functions involved are something that you do not know how to find the antiderivative of, then they can't be the dv and they must be the u. That's not an issue here because both functions, the polynomial and the e to the x, are functions that we can differentiate and integrate easily. So the next question is, which of those functions gets simpler when we take the derivative? Well, e to the x does not get simpler when we take the derivative. It gets the same when you take the derivative. On the other hand, the polynomial, 5x squared minus x, gets simpler because the powers will go down. If you take the derivative enough times, you'll have just a constant, or even a zero. So the polynomial, 5x squared minus x, is a good choice for you. 5x squared minus x. Whatever's left over must be our dv, so that is e to the x dx. As usual, we'll just need to find our du by differentiating our u. The derivative of 5x squared minus x is 10x minus 1 times dx. We're doing this usual funny form of implicit differentiation that we do whenever we do these kinds of problems in the service of solving an integral. And we'll need to find the antiderivative of our dv to get v. The antiderivative of e to the x is just e to the x. So our new version of our integral, this integral equals u times v, that's 5x squared minus x, times e to the x, that's our u times v, minus the integral of v du. Our v is e to the x, and our du is 10x minus 1 dx. At this point, you might be feeling a little worried, because this integral is still something hard to solve. If we knew how to handle an exponential function times a polynomial, we would have already handled it in the original integral. We don't know how to handle that, and we still can't do it now. This is not actually an integral that we know how to solve. What do we do? Well, we can still use integration by parts to solve this new integral. We'll have to use integration by parts twice overall to solve this problem. Every time we do that, the integrand will get simpler, and eventually we'll have an integral that we do know how to solve. So let's take a second round of integration by parts. What should we use for u and v this time? We're not going to worry about the non-integral part, just about the integrand. Well, we could use e to the x for u and 10x minus 1 for the dv, but that's not going to work. I'll show you why in a different video. Let's use, for our u, let's use the new polynomial that we have here, 10x minus 1. And for our dv, everything left over, which is e to the x dx. And again, we will differentiate our u to get du. That's going to be 10 dx. And we'll find the antiderivative of our dv to get v, that is e to the x. And our new expression now, we'll have to keep all of the old stuff that was there. That's 5x squared minus x times e to the x minus whatever this integral is. Notice that we're replacing the integral with a new expression, but the whole thing is being subtracted. So give yourself some nice bit of parentheses or brackets here. Our new uv, that's going to be 10x minus 1 times e to the x minus the integral of v du. So our v is e to the x, and our du is 10 dx. And now we're ready to solve this. So let's get rid of those brackets on this round as well. We still have the 5x squared minus x times e to the x. Don't forget to write that. If you stop writing that part down, you might forget to include it in your answer, and you have a wrong answer. Minus 10x minus 1 times e to the x, minus a negative, so let's make that a plus. The integral of 10 e to the x dx, well, that's easy. That's just 10 e to the x. And of course, this is an indefinite integral, so we have to add a constant. This is our answer. We could write the solution right now. We could put a box around it and be done. But it might be nice to just clean it up a little bit and simplify it. Notice that we are adding and subtracting a bunch of terms, all of which are some kind of polynomial being multiplied by e to the x. So perhaps let's factor out the e to the x, leave that plus c there, and let's just combine our whole polynomial here. We have 5x squared minus x minus 10x minus 1, that's minus 10x, but actually we're adding 1, and then plus 10. All that times e to the x plus c. We can simplify our polynomial even more by combining like terms, and we have 5x squared minus 11x plus 11, all times e to the x plus a constant. This is the simplest form of our solution. As always, you can check that this answer is correct by differentiating this and making sure that you get 5x squared minus x times e to the x. You'll have to use the product rule to differentiate this, and when you do that, you will find that you end up with the original integrand. Let's talk about how you can tell that using integration by parts more than once was going to work here. This problem was the integral of 5x squared minus x times e to the x dx. As you gain experience in solving integrals using integration by parts, you'll see that if you have a polynomial part that's one of the functions being multiplied in your integrand, that will usually be the u. And if you have to do this process more than once, you'll keep using the polynomial part as u. And every time you do that, you'll differentiate it, and the power will go down. Since the degree of this polynomial is 2, you'd have to differentiate it twice to get down to a constant. So the degree of that polynomial is 2. What that tells you is you need to use integration by parts twice. What if we wanted to solve the integral of x to the 10th power times cosine of x dx? Well, again here, this is a function, this is an integrand, that it makes sense to use integration by parts because you have a product of two apparently unrelated functions. And one of those functions is a power function. If this were a different polynomial with more terms, but whose degree was 10, you'd still probably make that polynomial be the u. So this will be your u. This will be your dv the first time around. And you'll have to keep doing integration by parts over and over and over again. Every time you do, if you make that power function or polynomial the u every single time, the power will go down every single time, and it will take you 10 tries to get that polynomial down to a constant, in which case you can just find the integral of the function. So this will need to use integration by parts 10 times. Here's a tricky one. One of our integral was x to the 30th power times the natural log of x dx. We already did an example a lot like this one. You might think, well, you're going to have to do integration by parts 30 times, right? But it turns out that for this one, it makes more sense to let the natural log of x be the u and everything else be the dv. The power on the x will end up going up because you're going to find the antiderivative of your dv. But when you find the derivative of your u, you'll have 1 over x, and you're actually going to have a simpler problem. You only will need to use integration by parts once. Give it a try and you'll see that it works.